Hello. So today we're going to talk about potential energy and electric potential. So we're going to call that U as electric potential energy, right? For electric potential energy. And recall in the Newtons, so we have U also for the gravitational potential energy. Or gravitational. Okay, so and that was U is equal to minus G M1 M2 divided by R. Right? So what does that mean? It means that if I have one mass M1, I have another mass M2. So the potential energy that they have is actually negative, and this is R, right? So when they are at infinity, when this M2 is going to infinity, let's say this is infinity now, R is equal to infinity. And that's when the potential energy is approaching zero, okay? So this is the potential energy that was defined in the AP Physics 1. So this is more of a global version. So we do have a local version, which is called potential energy is equal to mgh. So that one, it's more for when your G is constant, but this is working for when the G also changes. Okay, so that's the U from the gravitational potential energy. And let's move on to the electrical case. So in the electrical case, if you have a plus and you have two plus, for example, right? So if you have Q1 and then Q2, the U is electric potential energy. It's defined as K, so Coulomb's constant, K, Q1, Q2, and then divide by R. And notice that there's no minus sign there. So you do have to plug in the plus and minus sign into here. So in this case, this is plus, that's plus. So then in this case, the potential energy for this two together, right? So this two is the system here. The potential energy for this system is equal to K Q1 Q2 divided by R, right? And the unit will be in joule, all right? And now if you have, let's say Q1 is plus and then Q2 is minus, then in this case, the potential energy will be negative, right? So then U in this case will be K Q1 Q2, but you have plus and minus and then R. Okay, so this will be negative, see that? So you can see Q1, Q2 is attractive force. So just like in the M1, M2 case, they are also attractive case, right? So this is also attractive force between the two masses. And then this U will be also less than zero. So it is consistent that whenever you have two that's attracting each other, physicists like to define them as negative. All right, so that is the potential energy for both mass and static charges. So we just did the potential energy. One is gravitational, one is electrical, and for mass, two masses, right? Two masses, and then for two charges, and these charges are static, meaning that they don't move. Right? So what if I have three mass, right? So M1, M2, M3, okay? So let's say if I want to move M3 away from the system, move it to infinity, you can see this one will attract it, and this one will attract it too. So there are two potential energy, and you need to add them together. So it's called superposition, right? Superposition. So you add them together, right? So you move this one away, and now you live with this too. Now you want to move this one away to infinity. Now this one will attract it. So you can see there are multiple potential energy that need to be added together. In this case, it will be G, M1, M2, R1, okay? This is R1 minus. and minus G M1, M3, R2, for example. M1, M3, let's call that R2, okay? And this one here, call that R3, and we minus G M1, M2, M3, R3. And you add them together, this is your potential energy, gravitational potential energy for the system, for this system here of the three masses. Okay? All right. So we're going to continue into the potential energy, electric potential energy for three static charges. So similarly, you got Q1 and then Q2. So you have R1 and then you have R2, Q3, and let's say that's R3, right? So you add them together, so you have K, Q1, Q2, R1, plus, remember, this one you have to put in the sign, okay? If this is plus, minus, minus, you have to put in those minus sign into it. And this is K, right? Q1, Q3 divided by R2. And then plus K, Q2, Q3, oh, this is R2. Q2, Q3 divided by R3. So that will be your potential energy for this system here. All right? Okay, so now we're going to move on to potential, all right? So for electric potential, it's also called voltage, right? Electric potential, it's also called voltage later, right? Voltage, right? So electric potential is using the V symbol, okay? So V is use of volume, is use of velocity. It's also here using for electric potential. Okay, so be careful. And electric potential is defined as the electric potential energy per charge. All right, so then you have K, Q1, Q2, R, and then you divide by, let's say, Q1 here, okay, Q1 here. So then that will give you K, Q2 divided by R, for example. So that is your electric potential definition. So let me give you an example. So if you have a charge here, and that's called a Q1, and it's plus, then surrounding this Q1, there will be potential. Even if you don't put a charge there, there's a potential there. And that potential, if you know the distance here is R, then that would be K Q1 divided by R. And you have to put in the sign. If this is plus, so then this one will be positive. If you have a minus sign, let's say Q2, and that's not here anymore. So this is a Q2. Let's say you have a point that you're interested. There's no charge there. There's no charge here, right? No charge here. And then this is R1, okay? And then at this point, P, this electric potential is equal to V, it's K Q2 divided by R1. And this is negative, right? So that will be less than 0. So it will be all negative surrounding, the electric potential will be negative surrounding this Q2. All right? So that is the electric potential definition. And hopefully that it's clear. I'll give you another example. So if you have plus and a minus, for example. So then let's say if you think about a point right there, then you have this one here, and this is R1. And this one here, this is R2. And let's say this is Q1, which is equal to 1 coulomb. And this is Q2, this is equal to 2 coulomb. 2 coulomb, negative 2 coulomb, okay? And let's say this is equal to 1 meter, this is equal to 2 meter. All right, so then how do I calculate the potential at this point P? All right, so V at P will be equal to K Q1 divided by R1 plus K Q2 divided by R2. So then you are putting your K 9 times 10 to the 9, right, with the unit, and then Q1 will be 1, and then divided by R1 will be 1, and then this will be plus, you have a K, and then Q2 is negative 2. And then you have this one 2, and then you add them together, and then you will find out this is less than 0. Oh, actually, that will cancel out, right? This is actually cancel out. So 1 minus 1. So this is actually equal to 0. At that point, this electric potential Vp will equal to 0. Okay, so you can see this is treated as scalar, right? There's no vector here, all right? So electric potential V is a scalar. Okay, not like E, electric field, which is a vector. Okay, all right. So we're gonna stop here until next time. All right. See you. Hopefully you having fun, and then.